This is a tutorial video for put some color in your life. So for the problem statement, we learned that we're given a table where it's basically symmetric. You have the same red rows, red columns. They are the starting rows, starting columns. And for each pair, they form a sum. And what we care, it's the sum of the digits for the blue numbers. It is original appear, we can only simulate this. So how does the sample input work for this table? 4 plus 4 end up giving you this 8, and 4 plus 49 give you this 53. So we break down those numbers into single digits. 8, 5, 3, 1, 6, 5, 3, 9, 8, 6, 1. 166124, and we find sum is 75. So what are the key observations? We care about the sum of the digits. So upon reading this table, we realize the table is n by n. So there is going to be inside the table, the blue numbers are n squared. If we are purely using brute force, it's n squared. We need to go through n squared number, breaking down this digit and sum them together. The blue number is formed by adding the row and column together, and the table is symmetric. The brute force is not going to work. You might be seeing some earlier, smaller sample cases, for example, when the AIs are less than 10. But otherwise, n squared is too large, not to mention this AI has to grow up to 10 to the power 15s. You likely have a sum of 10 to the power 15. So that means you have 15 digits inside every blue number where you have to use a loop to breaking it down. So brute force is not going to work. What are some of the key insights I have observed for this question? So let's look at the case when the digit sum after the summation is equal to the digit sum before the summation. What does that mean? So let's look at the example of 4 plus 4 equal to 8. So on the left-hand side, it's the digit sum before summation. On the right-hand side, it's a digit sum after summation. So 4 plus 4 is actually equal to 8. So in this case, we realize the digit sum before the summation is basically equal to the digit sum after the summation. What are the other cases that the statement might be true? So let's look at 4 plus 12 equal to 16. So the digit sum, if I'm breaking down the left-hand side, is 4 plus 1 plus 2. So it's going to be 7. Digit sum after the summation is going to be 1 plus 6. This also gives us 7. So you may tend to conclude that the digit sum after and before the summation are the same. This is correct for some of the cases, but not true for, let's say, 53, where you generated from 4 plus 49. So 4 plus 49 is equal to 53. So what is the digit sum beforehand? It's 4 plus 4 plus 9, 17. On the other hand, it's 8. What happened? So the decrease comes when this 4, when added to 9, it makes to a carry. Because if there's no carry happen, I would have like a 10 at this place. I lose nothing. But because I had a carry, and then I'm left with 3, so there is a minus 9 occurred because of the carry. Because carry happened when you have a sum of 10. But you only made a plus 1 to the higher digit. So you basically lose 9 in this sense. So we realized when there's one carry happen, we lose 9. Let's think about an example where there is 2 carries happen. So let's look at the cases where I have two carries happen. So let's say 199 plus 4 is equal to 203. So here you had a carry from the tens digit to the ones digit to the tens digit, and another carry from the tens digit to the hundreds digit. Let's see how many nines we lose. Um, Ideally, you wouldn't lose since you have two carries, you made to 10 twice. The number should has turned into 10. If there is a digit, single place digit that represent 10, however, there is not. So it's the 10 reduced to a 1 in a higher digit. So you will lose 9 for 2 times. So basically, we would imagine we have lost 18 for the digit sum. Let's check it out. So 199 is 19. And plus 4, this give us 23 for the digit sum. On the other hand, it's 2 plus 3 is 5. Well, we see indeed we actually lose 18 in the digit sum. Then we can safely conclude that if there is no carry happened, then the digit sum after and before the summation is going to be the same. But when there's carry happen, we lose 9 for each one of the carries. So we have leads to this important property here. It's the digit sum for any pair of number is going to be the digit sum for A and the digit sum for B minus the number of carries happen. Well, with key insights, the problem basically reduced into a deep problem where you add, let's first count the individual digit sum for all the numbers. So you have the individual digit sum. Let's say 4, I breaking down those rows because they are symmetric. The rows and columns are symmetric. Let's break down the number 49. Let's break it down into 4 and 9. And let's break down 12 into 1 and 2. Let's break down them together. And every digit is contributing. So let's 4 is contributing to all the numbers row-wise, since this 4 is added to every number in the row. So this 4 is added n times row-wise. On the other hand, the every digits from the row is being added to the columns n times. So in total, every single digit from the row, from the columns, is used 2n number of times. So let's first break it down the input row column by single digit. And every single digit is contributing to the final sum 2n number of times. So let's assume we have finished the counting. So each digit is contributing to a number of times. We need to correct for the carries. So for each digit position, there are multiple ways you can have carries. You can have carries from the ones to the tens digit. You can have carry from the tens to the hundred digit. You can have carry from the hundred to the thousand digit. So let's count those carries one by one. So how to count carries at the digit position W? So let's say if I only look at 49 and 4, I would like to know how many times this 49 will incur a carry to the tens position and to the hundreds position. Then I need to break down this 49 into tens. I first need to only look at this 9 so I can research into how many times this 49 is adding up to all the possible pair that end up to a carry in the tens position. So if I only look at 9, I will be finding some other numbers that ending up with ones digit greater or equal to 1. Because, for example, I can have 41 plus 49. This give me a carries in the tens digit. I can also have 32 adding up to 49. That's also giving me a carry in the 10th digit. That basically telling me I have to look at each position one by one and find how many possible pair, how many possible like complementary number can cost me a carry for each ones places, carry to the tens places, etc. So what do I do now? So I need to extract the ones digit, the hundreds digit, the thousand digit. So for example, what do I mean here? For the digit position, I want to keep the last one digit, last two digit, last three digit, last four digit. Let's say my number is 37,456. I want to look at the ones digit, which is incur the carry to the 10. I would mod 10. This mod 10 would give me 6, which is the ones digit. And then to get the last two digit, I would do mod 100. This give me 56. So with the last two digits, I can research into what are the complementary partner that can incur a carry to the 100. So in total, I would have 15 or 16 such arrays. So I have the number from 1, 2, 3, 4, 5, etc. until 16 positions. Since AI is from 1 to 10 to the power 50, you could have a carry when adding two AI together. So you will have 16 such array where each array is storing the last few digits from an input number. We want to sort the array B. So the B is from getting the last few digits. Why do I sort this B? Because for each number in this BI, I want to look for how many pair the BJ is going to be causing a carry. So we know, for example, when I am looking for carry to the hundreds digits, you want to look for carry to the hundreds place. Then let's say my number is 49. I'm looking for a complementary partner that is at least greater or equal to 51. So I want to know how many number in my N have the last two digits greater or equal to 51. So for each carries, I know the threshold. And I know the complementary. So this is going to be my threshold. And this is my current number. The result is the threshold. I want to know how many partners are actually greater than the threshold that will cost me the carry. So with binary search, this can give you all of n log n time because binary search requires your array to be sorted. That's why we sorted in the first place. And now after the sort, it will give you the index of the first number who is greater or equal to the threshold. Now from the index, then you can +1 that give you exactly how many numbers that are greater or equal to the threshold. Then what is the time complexity for these algorithms? The time complexity for each digit position is, let's say you have the ones digits for all the numbers, for all the integers. Then for every one of the integer, you want to know how many partners that can cause carry to the tens digit. First, you need to transform it into the ones digit, and then you need to store the ones digit array that's all n times log n for the sorting. And then to find how many partners are actually greater than the threshold for binary search, it's n log n again. So the total runtime for one digit position is n log n. But since you have 16 digit place, you have the ones digit place, you have the last two digits to research into how many carries you made to the hundreds, and then you have, let's say, the array that contains 3 digits to research into the carry that made to the thousand. In total, we can possibly have 16 of it, because the AI, every individual input number is roughly 10 to the power 15. If you add up two together, they could end up being there are carried to the 16. So roughly 16 of them. So the total runtime it's time 16 for this to calculate how many carries you have. The complete algorithm would be first you overcount without carries. So for each AI, the input, and then for each digit in AI, you add up the sum together because each digit is contributing to a number of times. And then you correct it for the carries. So for the digit position from 1 digit to 15 digits, you create the array B to store the last few digits, and then you sort it to prepare it for binary search. And then for each number, you research into how many partners can create a carry to the next higher digit positions, and you minus the count. Pseudocode-wise, this question, this implementation is quite hard. So I want to create the pseudocode for this question. Phase one is you count assuming there's no carries. So you first read through the n, and then you create an array of vector to store all the numbers. And then you want to go from 1 to n altogether, like going into every number one by one. And you get the last digit, and every digit is contributing to a number of times, and you get rid of the last digit until there's no digit left for every one of the input digit. And now the second phase is you correct for arrays at each position. So first I want to look for the ones. So my value is 10, and this 10 is growing into 100, 1,000, 10,000, so I can look into carry into the tens, carry into the 100. Now for the width, I create the B. The B is basically the last one digit, the last two digits, the last three digits for all the input numbers. Now in total, I have 16 of them. After I get the last digits, I store them. Let's say this B is the last one digit of all the n. So 4, 9, 2, etc. I store them. And my first input 4, I'm looking for all the complementary partner who has the last digit greater or equal to 6. So first I compute the threshold. Exactly, I'm researching into the carry into the 10. So this is my carries, the place sum that will include the carry minus myself. Then that's the threshold I'm looking for. This threshold will cause carry. So I want to find the lower bound function from binary search will give you the index of where the first number that is greater or equal to the threshold. And then the count is going to be n minus the index minus plus 1. And then that's exactly how many carries you could happen. And then you minus 9 times the number of carries that could happen. And then you move on to the last 2 digits, last 3 digits, etc. And you finally output the answer.